I'm Olivier from Ubisoft La Forge, and today I'm here to tell you how we can use reinforcement learning to help us make better games. And more precisely, my objective today is going to share our experience in training bots with reinforcement learning techniques with the goal to assist some of our productions. And please note that reinforcement learning can be used in games for other things than training bots, but my focus here will really be on bots and AI. I'll start with a brief introduction to what reinforcement learning is and how it can be useful in games. Then we go through a series of examples of how to integrate reinforcement learning algorithms in an actual commercial games. And for each of these, I share some practical tips that I hope you will find useful if you want to get started in this field, which I definitely encourage you to. So let's get started with what reinforcement learning is and how can we use it in our games. Unless you've been living under a rock, you've probably heard about these impressive results by OpenAI on the mobile game Dota 2, where they managed to beat some pro-level players with an AI that was trained with reinforcement learning. And more recently, earlier this year, we've seen the AI AlphaStar by Google that was also able to play some of the best StarCraft 2 players in the world. So beyond this media hype, we can also see that we have today 2 reinforcement learning talks at GDC, so definitely the industry is starting to pay attention as well. So as a game developer, when you see this kind of really cool results on Dota 2 or StarCraft, the first application you may think of reinforcement learning is probably going to be to use it in order to build your game AI. And that's actually not a new idea. Reinforcement learning has been around since at least the 90s. And if you search a bit online, you may see that, for instance, back in 2001, Black and White shipped with some reinforcement learning in it. Although that's actually the only example I was able to find by searching the internet. At least I just learned last week that in 2016, Blade & Soul did ship some AI with some reinforcement learning components as well. So there are probably a few more, but I think it's fair to say that today, reinforcement learning is not definitely something that everyone uses in game AI. And there are good reasons for this. Reinforcement learning turns out to be a pretty tough beast to tame. So, when your goal is not just to win, but to actually have a fun AI, you have a lot of constraints, and maybe a technique like error is not the best one. So this brings me to my second family of potential applications, which is to help us better test our games. So for instance, let's say you have a large open world games with many systemic components, so your player can go in a lot of different places, can interact with the world in many different ways, and testing everything just becomes a real nightmare. So to help you with this, you may think of training an AI to play the game like a player would, and then collecting lots of data to detect potential issues. Similarly, maybe working on the live multiplayer games, constantly adding new characters, weapons, gadgets. Again, it's very hard to fully test everything, especially when you want this game to be really balanced. You don't want to have any exploits. So this is another case where having an automated AI that does testing could help you with. So for this kind of applications, what's cool is that this AI does not necessarily need to behave perfectly. It's not, you don't have as many constraints as for player-facing AI. So it may be easier to deploy this kind of reinforcement learning techniques. So I just told you about some potential applications. The focus of this talk, more concretely, will be on some practical implementation of these ideas in some prototypes that we've been building at Ubisoft, whether it's with the goal to have some player-facing AI or to help us better test our games. I still haven't told you what reinforcement learning is, so probably a good starting point. Please note this won't be a technical tutorial on reinforcement learning. So I'm just going to keep it very high level, but I do want to give you some intuition about some core concepts behind reinforcement learning algorithms. So at high level, reinforcement learning is about sequential decision making. And what this means is we're going to consider a setup where we have an agent interacting with the environment. And if your goal is to build some game-playing AI, the agent is going to be the AI controlling the bot you want to train, and the environment is just going to be the game that you want to play. Reinforcement learning works in discrete time steps. At each time step, the agent is going to perceive a state from the environment. That's basically what it observes. And we're going to see various ways to represent these states. So here in this specific example, let's just imagine just a set of two Boolean flags that indicate whether we are seeing an enemy on the screen and whether we are aiming at an enemy. From this state, the agent needs to take an action. So maybe here, for instance, our agent can aim at an enemy or shoot at an enemy, and he's going to fire, so that's a shoot action, fire. Then on the next time step, the environment is responsible for resolving this action and sending the updated value of the state. So let's say here, for instance, the agent fired, killed its enemy, so now the state has changed. And along with the updated state, the environment is supposed to send a very important signal that's called the reward. So the reward tells the agent how good it's doing. And as an agent, my goal is going to try and maximize the total sum of rewards that I can accumulate over the course of a game. That's the goal of reinforcement learning. And what any reinforcement algorithm will do is try to find this mapping from state to action so that I get as many rewards as possible. So that's basically reinforcement learning in a nutshell. I do want to introduce one extra concept, which is the concept of a Q-value. So the Q-value is a single number that you associate to a pair of state and action, and it represents the future total reward that you will get if you take this action in the given state. So please note, importantly, that it's not just the immediate reward on the next time step. So it's really the total sum of reward that you may expect to get. So for instance, let's say here I have an aiming action. Aiming doesn't give me any immediate reward, but because it puts me in the state where I can shoot at my enemy and get some reward, maybe the Q value of the aiming action can still be positive, even if the immediate reward is 0. So it's really, it tells you everything you're going to get in the future. And the reason why you may be interested in computing these Q values is because if you know them, then this idea of finding the action that maximizes the future reward just can be redefined as picking the action that maximizes the Q value. It's really just a way to rephrase the problem. We still haven't solved it. We still need to actually compute these Q values. That's the hard part. And that's what reinforcement learning algorithms are actually trying to do, at least some of them. So if we have some AI programmers in the room, they may be thinking, this kind of problem can readily be solved with some traditional techniques like a search algorithm like SR, or maybe a planning algorithm like goal-oriented action planning. And that's definitely true. And the way you do that as a programmer typically is you would sit down and implement some data structures and functions so that you can navigate the state space. So here the states are the nodes on my graph. You would have some actions to transition between states, and you would define as well some kinds of goals that you want the agent to reach, and maybe some traps that should be avoided. Then at runtimes, your agent is going to basically search this state space. It's going to do that by using your data structures and functions to simulate the effects of the future effects of the actions, and find its optimal path towards its goal. That works pretty well, but it does require this expensive search at runtime. So let's see what happens now if we were to solve the same problem with reinforcement learning. So here, the offline phase is actually going to be the training of the agent. And the way it's going to work is basically the agent playing the game sequentially until the end, and doing that many, many times, collecting a lot of data, and for instance, try to compute these Q values I mentioned before based on this data. This diagram makes it look like it's fully automated. It's true to some extent, but in order to get this fully automated pipeline, you will need to combine both some programming expertise as well as scientific expertise. So it can take some work to actually make it work. If you do manage to get it to work though, the benefit is now at runtime, when your agent needs to take an action based on its current state, let's say it's computed these Q values, then all it needs to do in order to find the best action is to take the action with the maximum Q value. So you kind of save a lot of time because you don't need to do this search anymore. You can think of the Q values as having pre-computed in some sense the outcome of the search beforehand during the offline phase. And something else that's quite important is you don't even need to search during training. So the training at runtime, it's only going sequentially through the game. So at no point do you need to simulate forward the effect of an action or to reset the game to a specific state. And these are features that could be very difficult to implement depending on your game. So in a nutshell, at this point, reason why hopefully you might starting to feel a bit excited about reinforcement learning. First, because it promises you to build your AI by you just providing some objectives through this reward function, and then the agent is going to figure out by itself what it should do in order to reach these objectives. And also that you may not even need to change the way your game is implemented. In theory, the agent should be able to play the game just from the player point of view and learn how to play it. So obviously, it's not magic. So there are some caveats to this, and we'll see some of them through the presentation. Now it's time to get started with the first approach to actually integrate reinforcement learning into your game. And I'm going to tell you about learning directly from the game screen. That's actually the approach that rebooted, in some sense, the whole field of reinforcement learning a few years ago in the scientific community, where it was initially implemented on a set of about 60 Atari games, and it was found to be able to perform above human level on many of these games with exactly the same algorithm and only the game screen as input, which is quite impressive. So as a game developer, when you see this, it's first, I want to tell you a bit more about the algorithm that you're going to use. So it's called the DeepQ network algorithm, or DeepQN. And I want to give you some high-level overview of how it works. So DeepQ networks, as the name suggests, it's a neural network that computes Q values. So if I'm playing Space Invaders, basically I have three actions: left, right, fire. So I'm going to compute these three Q values as output of a network, one for each action. And I'm going to do so with the state as input, because remember, the Q value depends on the state. So here my state is going to be just the pixel screen. And actually, in practice, typically we're going to take as input the last few frames. This gives the agent the opportunity to have an idea of how objects are moving on the screen. Then the mapping from state to Q value is going to be through a series of mathematical computations. So it's the same kind of layers you may find in any kind of other neural networks, especially in computer vision. Then the goal of the learning algorithm will be, from the data collected by the agents on state, actions, and rewards, to find the actual weights of this network so that the Q values are properly estimated. And once this is done, if I want to know which action to take in a given state, I just need to look at the output of my network and pick whichever action has the highest value in the output units. That's basically how it works. And this is super attractive to game developers, because all you need to do basically is take your game, plug the display on a generic reinforcement learning algorithm, plug this algorithm some kind of virtual controller, and then you can play in-game. It's entirely generic. You don't even need to access the code of the game. However, this approach was demonstrated on Atari games, which are pretty basic. Now graphics are a lot more complicated, so that means the state space is a lot more complex. And we also have analog controllers with tons of buttons. That also means that the action space is a lot more complex. So it's not that clear that you can scale the same algorithm to modern games. It's still actually possible to some extent, and I want to show you some pretty interesting results from EA Shield, where they built some prototype on Battlefield 1, and they actually addressed exactly this issue. So the first one about graphics, basically what you want to do if you want to learn from pixels is actually simplify the graphics. So degrading the textures, downscaling the input. And then it's really required if you want to be able to learn this neural network directly from pixels. The other issue was the complexity of the input. So this is an issue. So one way to do it is what they did. They took this reinforcement learning pipeline in black, and don't try to understand everything there. Just trust me, it's very generic and standard reinforcement learning pipeline. The key ingredient is they added on top of it this imitation learning pipeline where they collect human data, and then the agent is also trying to imitate what a player would do in the same situation. And that's extremely useful because now instead of randomly smashing buttons to figure out what's going on, the agent is actually going to take some inspiration from player data and is going to learn a lot faster. So it can work to some extent, but there are some more challenges as well, and I want to illustrate them through some work from my colleagues at Ubisoft Pune, who've been working on building a bot for automated testing in the game Steep. So here, what you can see in the top left is the agent playing the game Steep, and the bottom right is the input to the agent. You can see it's running at a lower frame rate. Also, it's only seeing what's inside the three rectangles. The reason for both of these is because otherwise computation would be too heavy. And I also want something, the first thing I want you to notice is there is a lot of red on the screen. So we have many red trees and obstacles. That's because, Steep is a snowboard game. That means there's a lot of snow. And you try to train a vision-based system where everything is white, it's actually pretty hard. So it was decided to kind of hack the textures to highlight better the objects so that we can actually see something. The other important thing is work is actually the AI is divided in two components. And the first one is a classical object detection system based on supervised learning. And that's basically the vision part of the agent. And the second one is really the decision-making module that's built on the detected objects. So here we don't have an end-to-end training from pixels to actions. It's divided in two. And again, the reason is because it's actually pretty costly to train everything end-to-end. So this is a way to make the decision-making task a lot simpler. Because if you get back to our original DQN algorithm, what you can think of it doing, it's really, intuitively, in the lower layer of the networks, it's going to build this vision system, and it's going to take a while to do so. And then the higher level of the networks are more about the decision making. And because you try to train both at the same time, this is pretty costly. Also, just having the image as input is a high-dimensional object, so if you have large neural networks, it can be slow. That's not even considering the fact you actually need to render the game, which also costs more GPU. There are some other more subtle issues with pixel-based learning, like the fact that, let's say, as an agent, I'm turning my head from left to right. Maybe I was seeing initially a white wall in front of me. Now I don't see it anymore. But does it mean the wall has disappeared and I should act as if it didn't exist? Well, probably not, right? So you need to kind of fake or have some kind of memory in your agent, so that adds another layer of complexity. And finally, if your hope is to be able to play any game from a downsampled screen, you probably discover that there are some challenges, like if you have some fine white details, like the amount of ammunition, maybe you don't see it anymore. If sound is important if you game for gameplay reasons, maybe you don't have access to it anymore. Also, I kind of conveniently avoided to talk about the reward, but if you want to know if you're doing good, you need this reward. If you want to get it directly from the game screen, it can be tricky, so maybe you will actually end up accessing your game code anyway. So all this to tell you that, yes, reinforcement learning is very attractive from pixels, but at the same time, it's a bit trickier than you may think, and it's going to be very computationally costly. So this brings me to my next part in the talk, which is what about directly learning from the game states? And by that, I mean building a training pipeline where your reinforcement learning algorithm can directly talk to the game. So now the state is not the raw screen anymore, but some kind of predefined data structure that contains all relevant data that the agent needs. And typically, this is something that's going to be much cheaper to compute. And maybe you can even turn off the rendering of the game so you can run the game faster. And since you're deciding what's in the state, you can choose to add information that maybe the agent does not directly observe, but that it should know based on its previous observations. And at the same time, it may be a good idea for you to replace this controller, so just accessing directly the controller buttons, but instead have some kind of high-level actions where you can inject some domain knowledge. So for instance, if you know your agent is going to need to move a lot in the world, then you could define a move action with some target position as parameters, and then when the agent triggers a move action, you can actually use some existing pathfinding algorithm to get to the right point, instead of forcing the agent to learn which exact controller buttons it should press to reach its target while avoiding obstacles, which is already just a very difficult task on its own. So to illustrate this idea, I'm going to tell you about 2 prototypes that we've built at Ubisoft La Forge. And the first one is an automated test pipeline for the AI in the game For Honor. So if you don't know For Honor, it's essentially a team-based fighting game where new heroes are regularly being added, and each of these heroes needs to be playable by an AI. So this means there's a lot to test because each new hero's AI needs to be balanced against every other hero, whether they are being controlled by a human or by another AI. And while we were experimenting with a reinforcement learning training pipeline in For Honor, we ran into this first example where we found actually a weakness in the existing AI. So here you can see in orange, it's our bot, Vatuchain, so let's call it the smart bot. It's fighting against an existing game AI bot in blue. And what you're going to see here, it's the bot actually stepping back. And then when this happens, the game bot sprints towards it. And while sprinting, the game AI turned out to be vulnerable. So again, it's going to step back here. Then the game AI sprints, is vulnerable, and our bots learn how to exploit that. So it found a very safe strategy in order to win. So when we saw that, we thought, oh, that's pretty cool. What about building a fully automated test pipeline in order to discover potential weaknesses in the game AI? So that's what we did. I want to tell you a bit about what kind of reinforcement learning loop we built. So in this setting, our agent is going to be, so the bot we're going to train. And at each time step, it's going to receive the state of the world. So in our case, the state is going to be like the health of the characters, their stamina, the animations being played, and so on. Then the action being taken by the agent is going to be chosen among the moves available to the character. And finally, the way we define the reward is the difference between damage inflicted and damage received. So if I'm trying to maximize my reward, it means I want to inflict as much damage as possible and take as little as possible, which should be a good way to win, right? By the way, you may think of using different weights on these 2 terms. So for instance, think like if you were to give more weight to the damage received, for instance, then you would get a bot that would behave in a more defensive way. So you can actually change the behavior of a bot by tweaking your reward functions, and that's what's called reward shaping in reinforcement learning. We'll see a few examples of this later. When we built our first reinforcement learning pipeline, we realized quickly that we needed to collect a lot of data. So what we did is we built this special map. So it's a map that's divided in 10 cells. And in each of these cells, we can host a single 1-versus-1 match. And this way, by having multiple agents fighting at the same time in the same game instance, we can collect a lot more data without having to actually run the game multiple times. Also, note that the game is running twice real-time speed right now, so this is also a way to collect more data. The architecture we used is pretty close to the one you can find in this paper, Distributed Prioritized Experience Replay. Here, each red box is going to be a Python process, so we use one process per agent. We use a single interface process to communicate with the game, just to minimize the communication overhead. And the important thing here is that all these agents dump all the data they collect in a single database, which is called the replay buffer, from which we have a learner process that computes the weights of a neural network, which are fed back to the agent. And then over time, they're going to play better and better based on this optimization process. So we implemented the pipeline based on this algorithm. I'm going to show you one example. So this is an excerpt of an email. We receive a few each day of these emails telling us what happened. Without going into details, the important curve here is the red one. It's the win rate, and it's basically pretty close to 100% by the end of training, which suggests that our bot has learned a reliable way to win its matches. And in order to know what's going on, the pipeline also gives some extra numbers. So for instance, here, they are the moves that are used the most often, and they are also the moves that inflict most total damage. And the one move I highlighted here in yellow is a special move. It's a zone attack by the SmartBot character. And it's the second most used move in the game, and it's responsible for more than 2/3 of the damage being inflicted. So just by looking at this, you may think that maybe the game AI has some trouble dealing with this move. And the report also contains a link to a video which we can watch to understand better what's going on. So here again, we have our SmartBot in orange fighting against the game AI in blue. Just ignore the green bar, they're just debug information. And here, this is the special move you just saw. Here again, this is this move. So this is the attack the bot is using. It's actually going to use only this attack during the whole match. He's using it again. It's the only time where it didn't hit. But it won't give up. So just, again, using the same move. Finally, again, yeah. So it used the same move 5 times. 4 times it hit, and it was enough to win the match. So if you know the game, by the way, it's not supposed to be such a powerful attack. So maybe a good idea to maybe boost the defense of the bot against this specific move. So, we have this pipeline running. It's working pretty well. But to do so, it required a significant amount of work. And we also had some failures along the way. And I won't have time to go into details of all the failures, but I do want to teach you some of the lessons that we learned along the way. The first one is, really, it's very important that you build a bug-free reinforcement learning loop within your game. So in our case, we run into this subtle issue where, in some specific situation, the game was actually changing the action chosen by the agent. And first, it confused the agent during training. And then it confused really the hell out of us as well when we were checking what's happening there. The agency is doing something, but the logs don't match. We didn't understand what was going on. We wasted a lot of time. So, add asserts, monitor everything, and especially don't trust just the reward going up as a sign of everything is working correctly. Because reinforcement learning is very good. The agent is going to maximize your reward, whatever it takes. It doesn't matter what kind of nasty bug you have under the hood, so you need to be very careful. Something else is we wish we had an ability to reset the state as well as to replay matches. First, resetting the state can be very useful for exploration. The idea is there are some situations that are pretty rare in normal matches. And because they are rare, you don't collect a lot of data about them, which means your agent doesn't really know what to do, and it may end up doing really stupid things. And if you can reset the state, then you can actually force these rare situations to appear more often just by resetting the game to these specific situations. Then you can collect a lot more data about them, and then you're going to be able to learn better policies overall, at least much faster than if you wait until you collect enough data naturally. And the ability to replay matches is really just, for us, it would have been for debugging purpose. We were mostly looking at logs, and sometimes it was very confusing and painful. Finally, last lesson, so keep in mind that reinforcement learning should be one tool in your AI toolbox. So in some cases, it can be pretty inefficient. There are other techniques you may think of, like search and planning, that could do a better job. So don't use reinforcement learning just for the sake of doing cool stuff, right? Like we did sometimes, maybe. And think about it before. A few more practical tips from this project. This is a pretty simple one, but you don't see it in research papers. So what you see here is on the top right, the list of all moves available to the agent. And the ones in red are these moves that the agent can't actually take just because of the rules of the game. It's a fighting game, so you have combos. Some moves can only be chained after over, so that's why this kind of stuff happens. And if you let your agent just try, the agent does not know about it. It's going to just try things that just have no effect in the game. And it's going to take it a long time just to realize that nothing is going on because it learns only from the reward, right? So if you want to speed up training, actually just prevent the agent from taking these actions. You need to modify a bit the learning algorithm, but it's pretty simple, and you're going to be able to learn much faster. And if for any reason in your specific game, you can't know that an action is invalid until it has actually been taken, then at least give a negative reward to the agent for trying these invalid actions. So this way, the agent will learn over time just not to try them. Something else, again, simple trick, but pretty useful in practice. It's what happens when you need to have a game where reaction time is important. So in fighting game, it's actually very easy to build a very powerful AI that's just going to react to anything the player is doing. But it's not really relevant because it doesn't represent the actual player experience. So one way to address this is simply to delay your actions from the time you observe the state and from the time you take the action. So it's kind of a crude approximation to what human decision-making is, but in many cases, it's enough for what we want to achieve. Finally, I want to tell you a bit more about reward shaping. So remember I told you before about how you can influence the behavior of the agent by changing how the reward is defined. So here I'm going to show you a bot that was trained with an extra bonus for performing a special move that's called guard break in the game. So it's a move that can stun the opponent. And the reason we changed the reward is because we thought our previous bot didn't use this move as often as we thought it should. And we thought, OK, maybe we can help it discover the value of a guard break, because when the opponent is stunned, then you can actually hit it. So here's the result. So actually, first a guard break. So this is a guard break. Again, so this is a guard break. And basically what happened here is our bot has almost killed its opponent, but it does not want to kill it. And the reason is because it discovered that by just keeping its opponent alive and just doing guard break, guard break, guard break, thank you, I can get more reward this way rather than killing it. So really, it's just an anecdote, but the point here is, no, it doesn't want to kill it. It just goes on for like a few minutes like that. It is going to find, any way you define the reward, your agent is going to maximize it, and sometimes not exactly what you expect. So this concludes the part on For Honor. Now I want to tell you about another completely different project, also from Ubisoft La Forge. And here the goal was to train an AI to drive in the Watch Dogs 2 engine. And the reason why we're interested in training a driving AI in Watch Dogs 2 is because in Watch Dogs 2, the AI vehicles were controlled by something called a PID controller. That's essentially a response curve that tells you how much, for instance, you should steer the wheel when you are that far from the road. And it works well. That's what's shipped with the game. The thing is, you need a lot of different parameters, especially when you have a lot of different vehicles with different physics properties. So it takes a lot of time. And we thought, OK, can we actually train a neural network to drive instead of using these hand-tuned PID controllers? So here, some results. So this is actually one such neural network that's driving a Watch Dogs 2 vehicle at high speed. Note that here, we're not doing any pathfinding, so we just follow a trajectory that's provided by the game. And the quality is essentially on par with what we would get with a PID controller, except that it can be trained automatically for any vehicle in the game. in order to reach this result now, we can't use the DQN algorithm I showed you before. So this is the DQN algorithm. Remember, so it's mapping from state to action. The reason why we can't use it is for driving, the action is essentially a 3D vector that contains value for acceleration, braking, and steering. And each of these numbers is a floating point number, so we can take an infinite number of values. And we can't have an infinite number of units in the output layer of our network. So we need a different architecture. So that's where the deep deterministic policy gradient algorithm comes in. I just want to give you a high-level view of how it works. The idea here is we still compute some Q value, but instead of computing the Q value for all actions, we compute the Q value for one single action. And we still have a state as input. Here, that's everything we need to know in order to be able to drive. Now, you may wonder, like, where does this action come from? It actually comes from a different neural network, which is called the actor. So the actor is doing the mapping from state to action. And the goal of the actor is to find the action that is the best one. And to do so, is going to find the action that maximizes the value of the first network, which is called the critic. So this is called an actor-critic technique. And this is what we use to obtain the results I just showed you. Although it didn't go so well the first time. So this is some of our first results trying to drive at high speed. That's not really what we wanted to. So what happened here? So in this DDPG algorithm, the way you train is that during training, you actually add some noise to the action output by the network. And the reason you add noise is because in reinforcement learning, you need to explore. And by that, I mean you need to find the best action, that's the optimal action in each state. And to do so, you need to try different things. So exploration is about trying different things, and that's why you add some noise. But at the same time, this noise needs to be small, because if you just randomly do anything in the game, most likely if you're driving, you're just going to keep crashing, you won't be able to learn anything. So if you visualize what's going on, so this is a 3D representation of my action. So let's say I'm driving at high speed, I'm reaching a turn, so I have a high acceleration, I have a low braking value. And the shaded area that you see there is going to represent the noise that I may be adding in order to explore different behaviors. But since I'm reaching a good turn, what I actually want to do is relay to brake, so lower my acceleration, increase my braking. So, and this new action, like the optimal action, it's actually pretty far from anything I may be trying to explore. So in the end, what the algorithm is doing this small exploration. It's not enough, it keeps crashing, and it's unable to learn the benefits of braking. So to solve this specific problem, what we did is something relatively simple, which is just to change the way we do exploration. So what we did is, because we knew it was important to brake, so we just say, OK, during training, we just set braking at 1 a bit randomly. And this was actually enough to solve exactly the task I showed you before. So this is after this change in exploration, it worked pretty well. And obviously, the important lesson here is not how to learn how to take a turn in a game. It's more that, more generally, in reinforcement learning, it can be very important to think about how you do exploration, because it can make a really big difference during training. And you should not hesitate to use whatever expert knowledge you have about your game to guide the agents toward the interesting behavior that you want to see. So from these two examples of learning from game state, compared to learning from pixels, remember, it's more efficient, it's usually more flexible. It does require you that when you interface with the game, you are very careful not to introduce any bug. And at the same time, it can still remain costly. Remember, you still need to run the game. And just running the game, if it's a heavy game, and maybe you want to distribute your game across many computers, that can be pretty costly in practice. So this brings me to the last part of my talk, which is, if your game is too costly to run, what about actually using a simulator instead? So that's what I mean by simulation. Replacing your game by something simpler that has the same behavior, but is going to be much cheaper in terms of computational resources. And the first thing you can think of is doing the whole training in a simulator, then taking your trained model and putting it into the game. I want to illustrate this with one example that we've been working at Laforge, and it's about training a swarm of drones. So in this application, the physics of a drone is so simple that it's pretty easy to just simulate it in this simulator that you see here. So what you're seeing here, the blue dots are the drones. They're trying to follow the gray objective while avoiding the black obstacles. And again, this is just a path following technique, so there's no pathfinding here. Main difference with what we saw before in the driving, first simplified physics, but now we have obstacles, and also we have multiple agents training at the same time. And having multiple agents training at the same time brings some challenges. Essentially what happens is, from the point of view of an agent, the environment is changing because the other agents are parts of its environment. So to illustrate this is a simple example, a toy example. Let's say you have two agents that want to reach the same objective. So maybe the first agent decides to go straight, then the second agent also decides to go straight, then they're going to collide. Then they're going to get some penalty for the collision. And so that next time when they reach the same situation, now the first agent, because it has seen this situation before, may think, oh, I know what the other agent is going to do, so I'm just going to go the other way around. But the second agent may do exactly the same. So again, oh, I know what the first agent is going to do, I'm just going to avoid it. And when both agents execute their actions in the environment, well, they're going to collide again. They're going to get a bit confused, and they won't really know what to do. So this is a very simplified view of what might happen, but the bottom line is, in some tasks, your training may become unstable because of this multi-agent learning. So you really need an algorithm that can account for that. And what we use here is a multi-agent version of the DPG. So this is just a reminder of the single agent version on the left. What we're going to do here is, and I'm going to just use two different agents to keep things simple, but you can extend it with any number of agents. We're going to use one different actor network per agent, but we're going to have a single critic network. So the reason why it helps is because the critic network, when let's say it needs to compute the Q value for the action taken by the first agent, it does not need to try and guess what the second agent is going to do. It has all actions as input. So it knows what's going to happen and can evaluate the quality of the action. And it's really just an intuition, but this is how we solve this non-stationarity issue. So you can think of this critic network as a kind of centralized brain that's coordinating the agent during training. And importantly, once the networks have been trained, these networks are decentralized in the sense that each agent just takes an action based on the state. There's no need for communication or for explicit coordination of actions. It's all baked in after training is completed. So this is an approach that was initially proposed in this research paper. It's a multi-agent DPG algorithm where each agent trained its own neural network. In our case, because we wanted in our swarm of drones, we wanted to be able to swap agents, we wanted to be able to add some, to remove some. So we wanted all agents to share the same actor network. So we implemented a version with shared network, which we called Clone Ensemble DPG. And at least for this specific task of drone swarms, it works much better than the original version. So we trained stuff in the simulator. So it's time to see what happens when we put them in a game engine. I first want to show you an existing algorithm. So that's Orca. It's used to solve this kind of problem. So here we have two groups of agents. And so they are characters, but just imagine they are drones, right? And each group is trying to go to the opposite side of the screen while avoiding the obstacles. Now compared to the same task, but now agents are controlled by the neural network that we trained before with reinforcement learning. And as you can see, this is a very different results qualitatively speaking. So in some sense, you may say like the Orca result is more robotic. The swarm, the reinforcement learning-based results is a bit more organic. And I don't want to claim that one is better than the other, but it gives different options to designers. They can pick whichever suits best their specific situation. One specific thing where the reinforcement learning approach can be particularly useful is it was actually very easy for us to extend it from 2D to 3D. So this is the result on 3D. And basically, we used exactly the same algorithm. We just had to change a bit the simulator. It was harder. And it worked pretty much right off the bat. So the message here is reinforcement learning, one reason why it can be super useful is because once you manage to get some good results on a task, and it can be difficult, but if you get to this, then usually you will be able to get also good results on similar tasks with very little effort. So that can be very interesting for us. So this sounds great, but as a game programmer, you may be worrying about the runtime performance of this approach. So we did some benchmarking. So here you're seeing the time it takes in microseconds to do a single prediction through the actor network for the kind of network we saw on the Swarm project. And we tried different implementations using different libraries. It's exactly the same network. The best result is with this run library, which is internal to Ubisoft. It's about 3 microseconds. That's on the same order of magnitude as the Orca algorithm I showed you before. So in short, it's competitive in terms of performance. If you're interested in how we got these results, look into the C++ keyword restrict, because it enables some pretty interesting compiler optimizations. Please do take this exact number with a grain of salt. So this is on one specific network. Also, it's doing only a prediction for a single example, and maybe some libraries here are better suited to batching, for instance. But the key message is, no, you should not be afraid to have neural networks in your game. You can actually make them efficient enough. Now, it may be the case that you can't build a simulator that's a perfect replication of your game. In that case, I still encourage you to work in simulation just for prototyping. And by prototyping, I mean trying different algorithms, see what works best, see what the best definition of state, actions, and rewards, because this actually takes a lot of time. And if you're working on a game engine that's pretty slow or just complex, you may waste a lot of time doing so. So I want to show you a couple of prototypes from simulation, also from LaForge. So the first one is a follow-up to the driving project we saw before. And the goal here is to augment it with the ability to handle maneuvers as well as avoid obstacles. So we've been working in this simple 2D environment, and the algorithm we've been using is a more recent algorithm than DDPG, so it's called Soft Actor Critic. And in particular, it's better at exploration, so it solves kind of the issue we had before with braking. And a maneuver is when you're at that starting point where the direction of the car is not aligned with the trajectory. So you need to go in reverse, do some U-turn. That's the kind of stuff you can learn. It actually does a pretty good job. We also avoid these yellow obstacles here in the middle of the road. The lines are just the sensors used by the agent to detect the obstacle. So you can see it works pretty well. To get these results, again, it didn't work immediately. So initially, we started from the same reward we had on the Watch Dogs 2 project, which is basically how fast you go forward times a term that penalizes the distance to the center of a road. So, to maximize the reward, clearly you need to go forward as fast as possible and be as close as possible to the center of the road, right? So that's almost what we saw when we learned it. That's actually the result. And what happened here is, it's actually going backwards. So the forward speed is negative, and it's so far from the center of the road that the second term is negative as well. And the agent is very happy with maximizing this reward. It's a bit difficult because it actually has no idea what's behind it, so it's pretty impressive, actually. And again, it's just a simple illustration, but reward shaping can be a bit tricky. So we fixed that by changing the reward, and now it works pretty well. Finally, another completely different prototype also from LaForge. So here, the simulator is a 3D environment whose physics are controlled by the Bullet physics engine. And the goal is to train a neural network still with reinforcement learning to control this ragdoll. And we want to mimic this motion capture animation while being robust as well to external perturbations like these red blocks that are being thrown at the character. And you can see it's working pretty well. The agent keeps dancing. It's not really perturbed, but it receives blocks in the face. So for this example, as well as the one I just showed you before on driving, we got this result in this simple simulation environment. And of course, the next step will be to take this algorithm that we saw were working pretty well. So here we're using the proximal policy optimization algorithm, yet another algorithm I don't have time to tell you about. The next step is going to actually retrain this in the actual game engine to get some more prototype that's closer to what we would have in the real game. I'm going to go very quickly on the last point, which is I just want to mention that you have something in the middle when your simulation is, so it's pretty close to your game, but it's not exactly the same as your game. What you can do is just pre-train a first model in the simulator and use it as a starting point to fine-tune it with the real game itself. And this way is going to be significantly faster than training everything in the game, even though you can't directly use the trained model from the simulator directly. So this is just be aware this exists. And this is going to conclude my tour of various reinforcement learning applications. In a nutshell, this is really my personal advice. Yes, you can learn from Pixel, but don't do it. Instead, try to interface with the game, but really be careful when you do that. It's very easy to miss something, so do it in a very careful way. And finally, if your game turns out to be too slow or too complex to work with, just do not hesitate to use a simulator instead. It can save you a lot of time in the long run. Hopefully, I managed to give you some excitement about what kind of stuff we can do with reinforcement learning in games, whether it's for player-facing AI, or for testing assistance, or for whatever new application we'll come up with. I want to conclude on some challenges that you will face if you want to use reinforcement learning. The main ones I identified, I'm going to repeat myself, but you need to have some kind of reinforcement learning friendly engine so that you can effortlessly integrate your reinforcement learning algorithm in your engine. And that means this bug-free and efficient reinforcement learning loop I've been telling you about. The other thing, I didn't mention it a lot, but depending on the task and depending on the algorithm, it may be very heavy on computations. So if you want to reproduce, for instance, the results by OpenAI on Dota or Google on StarCraft, they've been using like hundreds of GPUs and thousands of CPU cores in the cloud. That's not the kind of resources that most game developers want to spend to develop their AI. So be aware of that and plan for your resources ahead of time. And finally, to echo maybe something from the previous presentation, one major hurdle of reinforcement learning is it's actually pretty difficult to control the agents. These neural networks are essentially black boxes. You can't easily tell why an agent is doing something. You can't easily fix it when it's doing something wrong. And the way you usually try to change the behavior of the agent is through this reward function. We saw through a couple of examples, it can be tricky. If you're interested in seeing more fun examples, you can check out this list. It's very easy for an agent to manage to maximize the rewards in totally unexpected ways. So that's all I have time to show you today. If you're interested in this topic, I encourage you to check out the PDF version of my slides. So I will add a few more content in it. I also want to thank all people involved in this project. So that's my collaborators at Ubisoft, as well as the students who came at LaForge for internships. And finally, thank you everyone here for your attention. Thanks. And I'm happy to take any question.
Hi there.
Yeah.
Oh. Is it okay? So I noticed that you found some kind of gameplay issues when you were testing this. Were you able to find any actual sort of like errors or bugs in the games? And do you think that that is promising use of this?
So we've mostly been focused really on gameplay, like AI-related weaknesses. No, to my knowledge, no, we didn't find any bug. I mean, we had some issues where like the pipeline was crashing, but it was crashing the whole production, so it wasn't just us. So I do think that that's an interesting idea. Like, how can you maybe give a reward to the agent for crashing the game, for instance?
Right.
We haven't tried that, but it could be something interesting to look into.
Cool. Thanks.
Hi, so my question is about what happens if you care about more than a specific small loop. So as for example, you were talking about your game where you have the two people fighting each other, and so you set your reward function to be the damage given minus the damage taken, but that reward function in and of itself doesn't encapsulate the entire goal of a fight, right? Because if you're near the end and you have half your life and the enemy has a third of his, it's worth taking more damage than you receive because you can still get the kill while staying alive.
Yeah.
So how do you take into account the holistic view there if that's what you really care about?
So the easy answer is to say, okay, just define the reward for winning the game. So for instance, you only get like +1 at the end when you win the match, or it's a multiplayer match when you win the whole thing, and 0 otherwise. The problem with doing that is your reward becomes very sparse, so the agent only gets a signal at the very end, and then he needs to kind of figure out through all actions he took through this whole duration, which ones were actually useful to reach, which one actually contributed to the end reward. So usually when you do that, training becomes a lot slower. So that's why it's usually much more efficient to find a way to give rewards very often to the agents, as often as possible. But by doing so, indeed, what happens is you bias your agents towards some behavior that might not be optimal with respect to the overall goal you wanted to achieve. So there's no magic solution to this, at least that I'm aware of. So it's kind of a trade-off. You need to figure out the right granularity of rewards and the right definition to get what you want without putting too much bias in your agent. So yeah, it's kind of one challenge with controlling reinforcement learning agents. Something else you can do is, kind of related. Maybe you have different things you care about, and you don't really want to collapse them to a single number. And there's some works that's called multi-objective reinforcement learning, and it relates to the Pareto front that we saw before in another talk, where you can trade off different objectives in order to, to have different kinds of behaviors.
Thank you.
Hi. First of all, that was excellent. Thank you very much.
Thank you.
My question is maybe a bit tangential to this, and it has more to do with the practicalities of implementing something like this. How do you do this without wanting to strangle an animator that changes the length of an animation, or a designer that changes the damage on a swing? Like, it just seems like you would be training constantly, and maybe you're really disciplined in Ubisoft, and all the studios I've been at, like, are atypical, but it just seems like shutting down essentially production on these things for a long period of time just seems like a non-starter.
So typically what you want to do is, indeed, you don't want to have too long training time, because otherwise something changes, it breaks your AI. If it takes you 1 week to get a new working AI, I think it's going to be a problem. I think in many situations you can live with some daily update. So I think if you can aim at being able to train during the night, even if it means like you distribute computations of a lot of computers on the floor, I think this can work. And I think it's actually, if you can make it work, then that's where reinforcement learning is actually super useful, is compared to hand-tuned AI, where anytime something changes, people are not aware of it, then the AI doesn't work. People don't really know what's happening. They try to figure out what's changed. That's actually very difficult. While if you can build this automated test pipeline, having it run fast enough, then you don't actually have to monitor this. It's going to fix itself automatically. Of course, yes, there's going to be a delay, and you need to make sure this delay is not too long.
Okay.
So in our case, like, we can train during the night, so that's fine.
Okay, great, thanks.
First of all, thank you very much for the great talk. I have 2 questions. The first question is, when do you think we'll be able to see the RL-based agents in For Honor? And if it is a little bit far away from now, what do you think is the biggest obstacle in doing so?
So when, I don't think I can comment on that, so I'm afraid I have to skip that one. The biggest obstacle, I think, is really related to what the last point I mentioned, which is, right now with what we see after training, so we see that yes, it has learned some good behavior, but it's still doing some stupid things in some situations. That's probably not acceptable for a player-facing AI. But actually, another one I didn't mention, it's the way we do the training right now. We use this DQN algorithm. DQN results in a deterministic policy. So in a given state, the agent is always going to do the same thing. For a player, that's not interesting, because initially maybe you get beaten, but then you learn the patterns, and then you find a way to beat it. It's always going to work. So if you want to have some competitive player-facing AI, you need to look into stochastic policies, maybe add some kind of game theory, maybe some kind of player modeling. If you look at what Google did for AlphaStar, for instance, they have this notion of Nash game thing, where they actually try to have different strategies so that a player cannot just learn one way to beat your AI and just be done with it. So that's a whole field that we haven't started exploring yet, but it will probably be required if you wanted to have it in the game.
My second question is about designing the neural network architecture for the training. So basically, I think from my personal experience, reinforcement learning usually takes longer than just traditional supervised deep learning. So oftentimes I start with my first initial neural network design, and then it would take like hours to train, and then it would end up fail to converge. So I was wondering if you have any tips or strategies you can share us?
So not really, that's definitely a challenge. So the iteration loop in reinforcement learning is pretty slow. So that's why I encourage using simulators that are pretty cheap, so that you can really do a lot. You probably need some kind of farm also using the cloud and try different kinds of ways. And by having a cheap enough simulator, you're not going to waste too much CPU power, and you can really focus on the training of the algorithm. So that's one thing. The other thing is try to learn from what others have been doing. I think I have one picture here of the network by OpenAI, for instance. And I lost my cursor, so I can't show it to you. Oh, yeah, here it is. No. OK, anyway, you can find online the network that OpenAI used. Yeah, I have it here. So that's the network. So it's going to be hard to read, but basically it's a very complex network. And you can really see when you look at the network closely in these little boxes, they really use specific components of neural network architecture, pooling layers, convolutional layers where it matters, to really focus on the specific. It's really based on their knowledge of what these features represent, what kind of action they want to output. And yes, it really matters. So if you're completely new, maybe look at what they've been doing. It can give you some inspiration. Otherwise, it's really just a matter of trial and error.
Okay, thank you.
Hi, thanks for the talk. I have a question. How do you factor out the difficulty of the game in the reinforcement learning? Like, you want the AI to behave differently if it's easy or hard and that kind of thing.
Yeah. So you can do it different ways. One way is, let's say you computed Q values. Instead of acting always according to the action with the maximum Q value, you can just say, OK, I'm going to take the second one or the third one. You can play a bit with that. You can change the reward function. So maybe you can change the reward function so that if your agent is winning too easily, it's actually bad. So you actually get rewarded for having some level of damage being taken, for instance. So it won't try to always win by a full margin. So that would be, I think, the main two ways. So either you really add some noise in some sense to your policy afterwards, or you really change the training itself through the reward.
Thank you.
And that's it. Thank you, everyone.